The next question of lead code biweekly contest 120 is find number of coins to place in tree nodes. So basically in this question we are given a tree. So let's see how it's given. So basically it is guaranteed that tree is rooted at node 0. So in the tree, nodes that are present are n nodes, which are 0, 1, 2, so on till n minus 1. So the tree structure is given as edges. That is, there is an edge between u to v. This is what is given, but the direction of the edge isn't guaranteed that it's from u to v only. Direction can be from v to u also. But it's given that it's rooted at 0. Because it's rooted at 0, we can give directions to the given edges which don't have direction by doing a DFS from 0. So that way we are basically given edges between u and v nodes, and uh, obviously there should be n minus 1 edges because it's a tree. Now we have an array called coins given, coins of I. So basically what this tells us, coins of I will tell us how many coins are assigned to ith node. Coins assigned to ith node. So this is what we have. Now for each node, we can actually give some coins. Basically, these are coins assigned, but they are not placed. So we can place some number of coins in each node. So the way we place, how many coins we need to place on each node depends on the following conditions. That is, first condition is if the ith node subtree has lesser than 3, basically if ith node subtree has lesser than 3 nodes, then we should always place one coin. Ith node's subtree has lesser than 3 nodes, then we have to place one coin. And second criteria is if ith node subtree has greater than or equal to 3 nodes, then we can place, then we have to place, then in this subtree, let's consider 3 nodes which have maximum number of coins. Basically, let's consider 3 nodes and find out the product of assigned coins of those 3 nodes, those corresponding 3 nodes. Then among all such product values, we should assign this subtree with maximum product. So basically, it's like in the subtree, assign it with the maximum product of 3 distinct nodes. And there can be a scenario where the product, no matter which 3 distinct nodes we pick, the product remains negative, right? So in that case, if the product remains negative, then we should put 0 number of points. So if it has greater than 3 nodes, put maximum product of 3 distinct maximum product of 3 distinct nodes maximum product of assigned coins, maximum assigned coins of 3 distinct nodes. If in case this value is negative, then put a 0. If it's negative, then we have to put 0 coins. So these are the conditions. So we should basically say how many coins are placed on each and every node. We should basically return a list or an array depending on the language we are coding. where that particular, let's call it as answer. Then basically, let's say we have some answer array. Answer of 0 should represent number of coins which are placed on 0th node. Answer of 1 represents number of coins placed on first node, and so on. So this way we should output a list or a vector or array depending on the language. So now let's look over the constraints. Constraints for this are n can be in the range 1 to 2 into 10 power 4, and edges list size should obviously be n minus 1 because it's a tree. And edges lists, each field will have two integers, because edge will be between two values only. And length, cost star is length will obviously be n because we are given with coins assigned to each node. So this way the input format is. So basically n is in the range 1 to, basically all other input parameters depend on n, and n is in the range 1 to 2 into 10 power 4 per test case. So basically, let's consider this tree as our input, and these are the edges. And for each node, we have the following corresponding values assigned to them. Let's see how we can solve it for this tree. Similarly, we can solve for any tree. Uh, I took a sample in such a way that it follows each and every case that we cover. Basically, I took a input in such a way that it covers each and every case. So now, in this, one thing that we can observe is, for any ith node, firstly, if ith node subtree size is small, so this one, yeah, if ith node subtree size is small, which is ith node subtree size is less than 3, then for sure it is just 1. This we can easily detect. We can just find out the subtree size of each and every node. Now, if ith node's subtree size is greater than or equal to 3, for this, for sure we should place the number of coins depending on based on the second criteria, right? According to the question. So if you look at the second criteria, we should place the maximum product of three distinct nodes, maximum product of coins assigned to three distinct nodes in the sub, right? So for that, let me say, for that, firstly, let us observe one thing. Observation is, in the final subtree, in the subtree of any ith node, if we know what is the maximum positive, let P1 be the first maximum positive, P2 be the next maximum positive element, P3 be the third positive maximum element, and let us consider negatives also. N1 be the first maximum negative, N2 be the second maximum negative, N3 be the third maximum negative. Right? So now we can observe that our answer, we can just say the maximum number of coins assigned using this 6 variables only, right? If you know what is the first maximum positive, second maximum positive, and third maximum positive, and in negative, we need not care about third negative also. If we just know what is the first maximum negative, second maximum negative, then it's enough, right? Because maximum coins we can assign could be P1 into P3, either this, or it can be N1 into N2 into P3. Right? assuming that these are in increasing order and this is also in increasing order, right? So this is how we can assign. Basically, in these two scenarios only we'll get positive number of coins. In all other scenarios, the coins will be negative because firstly, if we consider there are no at least there are if there are no three positives at least, then for sure what we can do is we can use two negatives and one positive. That will make the result positive, right? So in case let's say we don't have two negatives and we don't have three positives also, then for sure we should use one negative and two positives to make the result, right? That will result in a negative number. So in that scenario, it will be zero. Whereas if we use three negatives, then still the result will be a negative. So we assign zero coins. Now, if we use two negatives and one positive, then it will be positive. So it's optimal to use two least negatives because their sign will become positive. So their positive value will get contributed. So it is product of two negatives into maximum positive that we have. So these are the two scenarios in which we can get in which we can get positive placed coins, and whatever positive placed coins we get, that will be the maximum in the subarray, which we can guarantee because we are already segregating them based on maximum positives and maximum negatives that we can pick, right? These are the maximum three positives that we have in the subarray for any ith element, and these are the smallest two negatives that we have in the subarray. Smallest two negatives that we have, and these are largest three positives that we have. So now it came down to just finding out what are the three maximum most positives in any subarray and two smallest negatives in any subarray. And once we know that, answer would be P1 into P2 into P3, maximum of P1 into P2 into P3, comma N1 into N2 into N3. Right? So, and one more thing, for this to be our answer, there should be at least three positives. And for this to be our answer, there should be at least two negatives and one positive. Then only these can be our answers. So we can just do a casework. If three positives are there and two negatives and one positive are there, then it will be maximum of these two scenarios. If three positives are there but two negatives are in there, then it would be this value. If there are at least two negatives and one positive, but there are no three positives, then it will be this value. If both of the criteria don't meet, then we need to forcefully place zero coins because for sure we proved that if we pick three negatives or one negative and some positives, we'll get a negative number. So for sure the product will be negative and we need to forcefully put zero coins. So this is the casework that we'll be doing. Now let us dry run for this uh, problem. Let us dry run for this tree. So firstly, let's find out the value for leaves. For 6, we place one coin. Okay, let me write it as this. Let's say answer, and this is for 0, 1, 2, 3, 4, 5. Okay, otherwise, let us write it per node. For particular node, what is the value? Let us write it in that simple. So for node 1, what is the value? Node 2, node 3, node 4. So, node 3, node 4, node 5, node 6, node 7, node 8, node 9, node 10, node 11, and node 13. So let's find out the answers for this. Firstly, let's come with the leaf nodes. Let us assume that we are doing a DFS in this fashion, and we can maintain the required data, that is maximum 3 positives and maximum and smallest 2 negatives while backtracking, right? Because we want the details in the subtree of every in the subtree for every fixed root of the subtree. So that is why we can maintain the data while we are backtracking. So now, assuming that, let's say we did a DFS and our control went to the leaf nodes. From the leaf nodes, we can see that from 6 will for 6 it will be 1, for 7 it will be 1, for 8 it will be 1, for 9 it will be 1, for 11 it will be 1, because we can see that number of nodes for these leaf nodes are only 1. So in that case we should put one coin for, so we should place only one coin. And for 12 and 13 also it is 1 because they are also leaves. So all the leaf nodes values are done. So now let us see for 4 what will be the value. For 4, if we see, we have only 3 indices, right? So for index 4, number of maximum 3 positives are nothing, and smallest 2 negatives are -10 and -3, right? So ultimately, because there are 2 negatives, and we should even have at least 1 positive to get a positive result, but there is no 1 positive. And one more scenario is we should have at least 3 positives, but there are no 3 positives also. So we can guarantee that for sure we can't get a positive result. So in this case, the value will be 0 because the result will be negative. Now for 5, if we look over, we have the maximum 3 positives that we have are 9, 3, and 11. And the smallest 2 negatives are empty, nothing. So for 5, the result would be 9 into 3 into 11. 9 into 3 into 11. And there is no one more scenario because for other scenario, there should be at least 2 negatives. As there are no negatives at all, that need not be computed. Similarly, for 2 also we can see for this index. While we are backtracking, we can just maintain the data of top 2 negatives and 1 positive, top 2 negatives and 3 top like minimum 2 negatives and maximum 3 positives. So here if we see, we have 1 positive and we have -12. These are the 2 negatives that we have. So if we look over, the result would be -12 into -11 into 12, because it will give us a positive result. -12 into -11 into 12. This would be the result of 2, because in the subtree we have only 3 nodes here. Now, if we look at 10, for 10, it would be 1 again. Why? Because there are only 2 nodes, and the criteria is we should have at least greater than 2 nodes. Basically, we should have at least 3 nodes. Then only we can apply those. We can apply the second condition. Now, if we look over the third node, in the third node subtree, we have -13, -20, and 10. Right? That means we have one positive, and the two negatives, two minimum most negatives that we have are -20 and -13. So if we look over, if we combine them, we get a positive result, which is 10 into -20 into -30. Okay. Now we have 1 and 0. So let's compute for 1. In 1, uh, 3 maximum positives that we have are, if we look over, we have 10, 9 and 11. These are the 3 maximum positives. And 2 smallest negatives that we have are -10 and -3. Okay? So -10 and -3. So here let's write them in increasing order. So 9 and 10. These are the things that we have. So that means the value for this would be 10 and this, and -10 and -3. Right? So these are the 3 maximum values. These two are the 2 minimum negatives. So because these set of values can contribute to both the conditions uh, that we derive to maximize the value, that is product of 3 positives or product of 2 negatives and 1 positive. So for this, the result would be maximum of 9 into 10 into 11. This is the scenario where we take maximum 3 positives. And one more scenario is the maximum most positive, which is 11 into -10 into -2. So these are the two scenarios. This is -3, okay, -3. So it would be max of 9 into 10 into 11, comma 11 into -10 into -3. And for 0, if you look over, so for 0, if you look over, the maximum 3 positives that we have are 9, comma, okay, we have 9, not 9, we have 10, 11 and 12. If we see 10, 11 and 12, and the maximum and the minimum most two negatives that we have are -20 and -13. -13. So the result of this would be max of 9, 10, 11, 12, which is 3 positive scenario, and it would be 1 positive, maximum positive, into 20 into -13, right? So this would be the result of 0. So if we look over, this is the maximum value in this part. And in the lower scenario, this is the maximum value, if we look at, right? So this way we can solve the problem. While doing DFS, maintain 3, while do perform a DFS from 0, to give hints how to implement, perform DFS from 0, and then maintain maximum 3 positives and minimum 2 negatives. While backtracking, return this. So at every ith node, we can maintain what are the maximum 3 positives in the subtree and minimum 2 negatives in the subtree. With that, we can find out the maximum, we can find out the points that we can place on the ith node. So if you look over the time complexity would be big of n, we can say, because we just perform a DFS and then we are just maintaining 3 variables. So we get n into a constant of 3 or 6, it depends on how we implement. Let us say the constant is n into 5, as we are maintaining 5 variables and uh, finding out the best value among the finding out the best 3 for every sub-array. So as this 5 is just a small constant, we ignore it and we say it's big of n. Practically, it would be 5 into n, but as we ignore constants in terms of big O, we say it's big O of n per test case. And space complexity depends on how you implement. Considering ideal situation, we can implement this in O1, and it can even be implemented in ON. So this way we can solve it per test case with a TL of big O of n and space complexity of big O of n. So, so one more thing here, that is we can either maintain while returning, we can either return the value or we can maintain if we implement it in big of n space, then we can maintain a global variable. And here I'm considering it as big of 1, assuming assuming like not bringing program requirement into picture. That is here when we are outputting, we need a list of length n, but that is program requirement. So I'm not including that program requirement in our space complexity. Apart from the program requirement, space that we need is big of 1. So it becomes big of n if we maintain global variables instead of returning variable by variable. I mean, for every ith node, if we calculate and store this data, then it becomes big of n. Instead, if we just store it when we are returning, because we don't require the other instincts when we are at ith node, right? We don't need any data of its children when we are at ith node, because its child's value is already computed. So we only need data of the ith node's maximum 3 positives and minimum 2 negatives. So that is why we need not store the child's value. Once we compute the child's value of any ith node, we can just we need not memorize that data. So if we implement it in that way and ignoring the program requirement, then the space would be big of 1. So this way we can solve it.